So my name is Deepak. I'm the CTO at Red Sift, a cybersecurity startup here in London. Today's sort of topic is very much what's in trend, serverless architecture. But I'll sort of go into why we picked it this way, and also give you a glimpse of how we think about architecture at Red Sift. So very quickly about myself, like most of you in the audience, I started my career as a developer. I still do a lot of hands-on coding. It's always exciting to do that. So I've tried to make the talk as exciting as I can for you. I started my career in the early 2000s. C, C++. So a lot of my time went into really waiting for compiling. Fortunately, that has changed a lot now. I don't think I need to wait for longer than a few seconds these days to get my code out. I've worked at various startups and a lot of big companies as well. So sort of that has shaped my perspective on how I think as an engineer, and both in the startup world and enterprises. Notably, Opera Software, the browser maker. So a little bit about Red Sift. We're a cybersecurity platform, underneath the product company that we are today. We're very much focused on email security, and we have two flagship products that sort of tap into help companies strengthen their email security. But underneath all this, we actually have a platform as a service. So you can actually build data-driven applications focused on cybersecurity on our platform. It's not yet public, but that's our long-term vision, to be able to build an ecosystem and a marketplace around this. And the way we've built our platform is very much inspired by the big data world. So you're actually working, a lot of you are familiar with GraphQL as well. So that's how your backend today for all our products is constructed. Data starts somewhere and then flows through a graph and then becomes something else by the time it comes out from the other side. So you can think of operations like MapReduce, scatter gather, or even simple aggregations. So very briefly, as every startup should, we started very much as a monolith. It was a big Node.js application that probably took us through until 2 years. We didn't really have to do anything special there. But once we started feeling the pain, we of course started our journey towards microservices. And of course, it always sounds like a great idea, but then you start to get into the nitty-gritties, and you start to see how it's not as simple as you thought it is. So that started roughly around 2015. We're pretty much still on that journey. We're not truly microservices yet. I like to call this stage the microlith. So we have the microservices, but we're still relying on a lot of centralized databases and services that keep it going. And of course, it's never easy, microservices. So you really want to do it only when you have both the resources and the need to do it. There's really no point in trying to prematurely get there. You want to stay on your monolith as much as you can. Our stack is fairly non-standard because we are on IBM Cloud. What used to be SoftLayer, the reason being we're a platform as a service. So our bare metals give us. We sort of rent bare metals from IBM Cloud and then layer our infrastructure on top. Because we do a few things around orchestrating the various computes that we need within our platform. We, of course, use Kubernetes to orchestrate the microservices. And predominantly, our backend is written in Go. But there's also Node.js and Python, which sort of augments it. And front-end is entirely in React. So coming to today's talk, and what we faced within our product was the classic. We needed to provide our customers with the ability to search within the product, and of course your classic approach to it is to put up an Elastic cluster, which works very well. But we wanted to, because our platform was very much built in the serverless architecture, we wanted to see how that would sort of work for us here. So, the problem statement was, we needed full text search and indexing. It had to be multi-tenanted so that, data from one customer is not mixed up with somebody else. And it had to be sharded for the same reason. Your customer's data had to sit independent of each other. So that's why we started, and we said, can we build something on our platform in a serverless way, and would it actually work without having to manage a cluster? So the reason to not have a cluster was mainly around operations. We already had a lot of operations from being on bare metals, having to layer Kubernetes on top of that, and then managing our infrastructure. Moreover, we wanted to move this problem from becoming a platform problem to stay within the product team, so that they could then manage this on their own without needing the expertise of the platform team. So we stumbled upon an embedded key value store. It's very much like a SQLite, which lets you have an embedded SQL server inside. So it's called RocksDB from Facebook. So it's a very popular project, historically built on the back of LevelDB, which was one of the first sort of the key value stores that came about. And the third reason being, we wanted to be self-contained, so that there is no search is not a 24/7 problem. People are not going to search on your platform for all the time. So that sort of blends into the serverless model. You start a function when you need it, you do your work, and then you're done, essentially. So the ingredients for this recipe essentially turned out to be RocksDB, which is the embedded key value store I was talking about. We picked up a Go library, which actually does the full text search and indexing for us. We had to layer a few things on top, but essentially the basic building blocks were available. Pretty much similar functionality to Elastic. It provides various types of attributes that you can index. You can have terms. You can have free text search. You can have tokenized search, of course. You can search through emails and domains, etc. So quite powerful. And infrastructure-wise, fairly simple. You just need a POSIX file system to sort of orchestrate the whole thing. Nothing fancy there. Whatever you send to RocksDB is essentially persisted on that file system. So very briefly about RocksDB, it's a Facebook open source project. They picked up LevelDB, but then realized for their purposes, it wasn't as performant as it could be. So they essentially rewrote it. And it's written in C++, so very portable. High performance, it's optimized for fast storage. We use SSDs, of course, to actually persist this. It's very adaptable as well. And of course, it does come with some constraints. The main constraint being you can only write from a single place. And that actually blends very well with the serverless architecture, because your function is invoked, can write, but then you can read from multiple places. Blev is the full text search and indexing library I spoke about. Very simple API, very JSON friendly as well. You can index any object within your data model. It's easily extendable. We had to extend it to sort of support IP addresses, because that functionality wasn't present in there. And file system, very simple. We just picked a network file system, mainly because we had to share it across our cluster of nodes. But the bottleneck is really your input-output operations on this. So staging, of course, we just picked a 200 IOPS, which is plenty. But on production, of course, to support our scale, we have about 10,000 IOPS today. And this is very extendable in the future. NVMEs are out there, so they support millions of IOPS today. So it's very easy to scale this. The only customization we had to do was supporting the IP address, because that was one of the attributes we had to index. So being able to store an IP, but query on the basis of a subnet. So saying that, give me an IP within this range, but also supporting IPv4 and IPv6. So fairly standard problem. We looked at how the other libraries did it and sort of implemented a similar one within the Blev library. There's no time for a demo, but I just gathered a little screenshot. So this is sort of where it sits within our product. There's a simple text field that sort of drops down various attributes for you as you search. There's also some deep linking, so you can come back into this interface with specific search terms and filters. And then what this does is fires off an API to our backend, which then invokes a function which starts and then has access to the POSIX file system I was talking about, and then can query RocksDB via Blev to give us the results. So, the prototype itself was fairly straightforward because our platform supported the serverless model. Unlike AWS Lambda, we've baked in sort of both persistence and it's easy to invoke other functions from one function. So because of that functionality, you can actually write some very advanced sort of data processing pipelines on our platform. So in that sense, this problem was perfectly matched for the solution. We were quickly able to prove that this sort of works. We've even written a blog post with sort of more technical details if you're interested. But once we had this, we of course ran into issues within production, of course, because whilst the single writer is fine, it just doesn't scale. So for our larger customers, we had to think of better ways to sort of scale this, and sharding is obviously the best way to do this. So we looked at tweaking both batching and sharding. So batching is when you can write a bunch of records together into RocksDB instead of writing it one by one. So we collect it and then we dump it into the database. And sharding is where we can actually sort of be clever about the single writer problem. It's a single writer, but if you can write to multiple partitions for the same customer, but then be able to read all the 5 partitions together, 5 or 6 or how many ever we configure as one unit, then we've solved that problem, because then there can be 5 or 6 writers, increases the throughput when you're writing it. But then when you're reading it, it doesn't have to care about trying to do anything fancy there. It behaves like those 5 parts come together as one single unit. And then of course our vertical limit was essentially the disk saturation. How many IOPS you actually hit it with in parallel. So what we did was very quickly benchmark various values of batching and sharding to see where the sweet spot for us is for our setup. So batching will increase the throughput, but it doesn't saturate the disk because you're actually writing in one go. So instead of writing 200 single records, if you do 200 of them together, that's essentially one write. And sharding, of course, allows us to increase the throughput, but of course it will saturate the disk because you're doing many parallel writes in the process. So this is sort of what we ended up with in terms of the benchmarks. So you see various combinations of batches and then shards being used. So these various colors are different batch sizes that we tried. So 20 all the way from 25 to 400. And the x-axis is essentially telling you how many shards we tried. So shards is individual pieces that we can write to. And on the y-axis, you see the throughput that we achieved on the back of this. So it escalates quite quickly and then starts to saturate. But for 400 batch size, we saw that it quickly degraded because you're trying to do too many across too many shards. So we roughly sort of settle down into whatever it was optimal for our use case, and we tweak this today as well. As we see it change a bit, we can do new benchmarks and then sort of tweak it to give us the best performance. So serverless, we didn't merely want to do this, just because serverless was the way to do this. We have bigger ambitions in sort of, like I briefly mentioned, we're pretty much a microlith. So we are still going to a central NoSQL database. So we wanted to use this experiment as a way to test if, for our application database, can we actually move away from a NoSQL cluster into a more serverless plus embedded database approach that I briefly explained here. So for us, this experiment was quite monumental because it showed us that our thinking, our architecture around serverless sharding actually could work for us in the long term, in truly sort of going into microservices. Where each of our services are essentially independent of each other as much as possible, and they can sort of survive failures across the rest of the services. So the sharding that we do, there's two levels, of course. One at the customer level, that provides natural security because we're then isolating each customer's data. It's self-contained, so we've moved the problem from infrastructure operations platform layer into product. So our product engineers today maintain this instead of our platform engineers spending time on this. And best benefit for us was operations-wise. There's no cluster to maintain. When a search happens, the serverless function does what it needs to bring everything up, does its work, and then it's thrown away when it's not needed anymore. So hopefully that gives you a glimpse of the way we approach this. Very iterative approach. Of course, we're big believers in iteration. You want to get something small out, see all the implications, see if it works for you, and then sort of put in more effort to scale it. Thank you very much. We're obviously hiring for various roles, so please do have a look and then apply.